Hi, welcome to the video. We're going to be having a look at the Hierarchical Navigable Small Worlds graph, or HNSW graph, and how it's used in vector search. Now, HNSW is one of the best performing algorithms for approximate nearest neighbor search. And what I want to do with this video is explore how it works and how we can implement it in Faiss. So let's go ahead and get started. Now we'll start with the sort of foundations of HNSW and where it comes from. So we can split approximate nearest neighbor algorithms into three broad categories: trees, hashes, and graphs. Now, HNSW, or it's HNSW graph, so we can figure out it probably belongs in the graph category. And more specifically, it's a type of proximity graph, which is simply means that vertices, which are just the vectors in our graph, or the nodes in our graph, are connected to other nodes or vertices based on their proximity. And we would typically measure this proximity using Euclidean distance. We don't have to, but that's the sort of standard. Now, going from a proximity graph, which is pretty simple, to a HNSW graph is a pretty big leap. And there's two main algorithms that have really helped me understand what HNSW actually does, and that is the probability skip list and the navigable small world graphs, which are just the predecessors of HNSW. So what I'm going to do is just quickly run through those two algorithms. So this is a probability skip list. It's reasonably old. It was introduced in 1990 by a guy called William Poog, and it works by building several layers of linked lists, which is what you can see up here. So what we do with this is we're looking for the number 11, or the key 11, and we start over here at the top layer of our start block. And what we do is we stay in our layer 3, which is our entry layer, and we move across. So we go over to the next block here, and we say, okay, number 11 is not 5, and 5 is not greater than 11. So we continue, and we go all the way over to the end block over here. Once we reach the end block, we know that we need to go to the next layer, so one layer down. And so we do that. We go to layer 2 at the start block again, and we continue moving across. Now, at this point, we get to block 19 over here, and we say, okay, 19 is greater than 11, so now we know that we need to go on to our next layer, layer 1 down here. And then we go across and we find number 11. Now, the whole point of this is when we have a lot of values, this can reduce the number of steps we need to take in order to get to our final value, rather than just going along our layer 0 and going along every single value within our list. And HNSW borrows this hierarchical layered format, or levels, as we will see pretty soon. Navigable Small World, or NSW graphs, were developed over the course of a few papers around sort of 2011s up to 2014. And the basic idea is that we can have a very large graph with many vertices, and because we have both short range links, so the sort of links that you see on the outside of our circle here, and we also have these long range links, which is what you see going across the circle, we make our graph very navigable. So it's very easy to get from one point to another in very few steps. And there's some terminology that we should cover here, which is all the vertices we have here, all of their connections, so all the other vertices that they are connected to, we refer to these as that vertex's friends list. Okay, and when searching this NSW graph, we begin at a predetermined entry point. So in here, we see we're sort of starting at a few different points, but in reality, with these sort of big graphs, we always start with one specific entry point, or maybe sometimes we can use different entry points based on some sort of logic. But we have either one or only a few entry points in our graph. And then what we do is we perform what is called greedy routing. Now, routing just refers to the route that we take through our graph, and greedy refers to the fact that we are always going to choose out of our vertices friend list, we're going to choose the friend that is the closest to our target vertex. Now, if we find that there are no near vertices in our friend list, this is a local minimum, and this is our stopping condition. We cannot get any closer. We're kind of stuck in that local minimum. Now, if our vertex has very few friends, we can get stuck quite easily. So we can get stuck in the local minimum if there are less connections. And we actually refer to vertices that have fewer friends as a low degree vertex. So it's low degree, it means it has a low number of links or edges. And then we also have high degree vertices. Now, with these, it's if we are currently on a high degree vertex, it's harder to get stuck in local minimum because we have more options on where we can move. Now, the routing through a navigable small world graph is split into two phases. So we have typically the earlier zoom out phase, where we are passing through vertices that have a low number of links. And then we also have the zoom in phase, where we are passing through high degree vertices, which have a lot of links. And what we tend to find is that high degree vertices will usually have more long range links. So we can move further across our graph with these high degree vertices. Now, to minimize the probability of stopping early, so avoiding those local minima, we can increase the average degree of our vertices. Now, this also increases the complexity of our network and therefore slows down our search time. So we have to find a balance between both of those. Now, another approach to avoiding hitting a local minima too early is to start the search on high degree vertices, so the vertices which have a lot of connections. Now, for NSW, we can do this, and it works for low dimensional data, but it doesn't work perfectly, and it's actually one of the key factors that HNSW improves upon and uses to improve its own performance. So let's move on to HNSW and how both those fit into HNSW. So HNSW is obviously an evolution of NSW, and it borrows inspiration from Pugh's probability skip list structure with the hierarchy. So you can see that here we have a few different layers. So we have our entry layer, just like we did with the probability skip list structure. And we also have an entry point. And what we've basically done here is taken an NSW graph and split it across multiple layers. So high degree vertices will tend to be spread across more layers, because when we're building our graph, we add the number of friends based on which layer it gets inserted at. The higher the layer that the vertex is inserted at, the more friends it's going to have, which makes it a high degree vertex. And what that does is, if we start at that highest layer, that means we're on high degree vertices. So we are less likely to get stuck in a local minima, and it means we're not going to stop early. So that allows us to start at the top layer, and we move through our graph. And what we do is we have our query vector, and on each layer we keep moving or traversing across different edges in that layer in essentially the same way we did for an SW. So we greedily identify the friend of our current vertex that has the least distance from our query vector, and we move to that, and then we keep doing that. And once we hit a local minimum, we don't stop the whole thing, we just move down to the next layer, and then we do it again, and we keep doing that until we reach the local minimum of layer 0, and that is our stopping condition. That's where we stop. Now that's how we search, that's what our graph looks like and how we search. But let's have a quick look at how we actually build that graph. So what we do is we have a probability function which essentially says we're pretty much going to put every vertex or every vector on layer 0. Not every, but a pretty high number of them, as we'll see later. And we say, okay, we get a random number from a uniform distribution, and if that number is greater than our probability for that level, we move on to the next layer, so we increment our layer. So let's say this turns out to not be true, we move up a layer and we try again. Okay, now this next layer is going to have low probability, but we're also going to subtract the probability value from our lower layer from the random number that we've produced. And we keep doing this again and again until we get up to our top layer. At that point, there are no other layers. This is very unlikely to happen if we, say if we have a billion, maybe not a billion, like 100, I think it was 100 million vectors that I tried this with. I got, I think, 4 vectors on the top layer. So it's very unlikely for one vector to go all the way up to the top. But if it does, we insert it at that layer, and it has the possibility of becoming an entry point for our graph. One other thing that we also have here is the ML at the top. Now this is called the level multiplier, and this value is just a normalization value which allows us to modify the probability or the probability distribution across each one of our layers. Now the creators of HNSW, they found that the best value for ML, the optimum value, was to use 1 over the natural logarithm of m. And m, we'll have a look at that pretty soon. That's just the number of neighbors each vertex is assigned. So here we have m, so we've set m to 3, and we're saying here, so we want to insert this blue vector. So that blue vector you see, we've decided, okay, we're going to insert it at layer 1. That means it gets inserted at both layer 1 and layer 0, but not at layer 2. And we go through our graph just like we do when we search, but this time we're trying to find many neighbors of our new vertex that we can assign to its friend list. And what we have here is, so with an m value of 3, we would add 3 neighbors to that vertex, both on layer 1 and also on layer 0. Now we can also have a m max value and an m max 0 value, which is what we have down here. And basically, as more vertices are added, we may find that this vertex ends up with more than 3 friends. And maybe that's fine, but what we essentially do is use m max to say, okay, if we have any vertices with more than this number of friends, we need to trim it, and we need to just keep the closest, like 3 in this example. And then mmax 0 is another value, and that is the same, so it's the maximum number of friends a vertex can have, but for layer 0, which is, I think, always a higher number than the other layers. Now, one other thing that we should cover very quickly is we also have 2 more variables, EF construction, EF search. Now, EF construction is used when we're building our graph, and it's basically the number of friends of our inserted vertex that we will use when traversing across layers. So in layer 1 up here, we have these 3 friends, and that means that during our search for friends in the low layers, we would go down like this. We would start our search from each of these 3 vertices in the lower layer. Okay, now that would be the case for all of those. And EF search is the same, but it's used during search time to search through our graph. And I mean that's pretty much all we need to know on the theory side of HNSW. So let's dive into the implementation of HNSW in Faiss. Okay, so we're in Python now, and all I've done is taken our data. So I'm using the SIFT1M dataset as we usually do, and all I'm going to do is use this to search through our index, as always. Now, the first thing we want to do is actually create or initialize our index. So I'm going to use 2 parameters. So we have D, which is the dimensionality of the SIFT1M dataset, so the length of our vectors in there, and also M. Now M, if you remember, that's the number of neighbors that we will assign to each vertex in our graph. Now, for this, I'm going to use a value of 32. And what we can now do is rewrite index equals Faiss index flat HNSW, and then we just pass D and M. And that's, we've initialized. Okay, sorry, so it's not flat HNSW, it's HNSW flat. Okay, there we go. So with that, we have initialized our index. Of course, there's nothing in there at the moment, and we can see that. So we can go ahead and write index HNSW max level to see, okay, how many levels do we have in our index? And we'll see that we get this -1, which means that the levels in there, the structure has not been initialized yet. And we also see that if we do this. So this is how we get the number of vertices that we have within each layer. So we write the Faiss vector to array. And in here, we want to write index HNSW levels. And then let's print it out. And we'll see that we just get this empty array. Now, what we'd also want to do when we do, so this is just a massive array. So if we will have 1 million values in here once we add our SIFT1M dataset. So what we do is we just write np bin count levels to count the number, to count basically how many vertices we have in each level. When I say level, by the way, it's the same as earlier on when I was saying layers. They're the same. So when I say levels, layers, same thing. So obviously at the moment we don't have anything in our graph. So how do we add that? We already know. We just do index add xb. Okay, nothing else. So we add that. That might take some time because we're building the graph we saw before. It's a reasonably intensive process. So it does take a little bit of time. I think maybe around 40 seconds for this. So I will fast forward. Okay, so it's done, 52 seconds, not too bad. Now, what we now want to do is, I want to have a look at these again. So let's see if we have a structure in our graph yet. So max level, so that's cool. That means we have 5 levels, 0, 1, 2, or up to 4. And then if we do this again, we'll be able to see the sort of distribution of vertices across each one of those levels. So I'll just write this. And there we go. So we just ignore this first one here. That doesn't mean anything. So this is our layer 0. Like I said, most vectors get assigned to this layer. And then we have layer 1 all the way up to layer 4 here, or level 4. Now, Faiss will always add at least one vertex to your maximum level, because otherwise we don't have an entry point to our graph. So there's always at least one in there. And we can also check which vector is being used there. So we can write index HNSW entry point. Entry point. Yes. And there we go. So that's the number of our vector that we have added as our entry point up here. You can also change that if you want, although I wouldn't probably, especially with this, I definitely wouldn't recommend it. Now, I was super curious as to how it decides where to insert everything. So went through the code, which you can find over here. So this is the Faiss GitHub repo. And we have this HNSW CPP file. And in here, we come down, and it might take me a little while. So this is where we initialize our index, and we have this set default probas. So if we go into set default probas, we will find this here, which is not really too hard to read. I don't know C++, but this is pretty simple. And what I translated that to in Python is this here, with a few comments, because there is no comments in the other file for some reason. Now, what we're basically doing is just building a probability distribution for each of our layers. And we do it using this function here. So we're taking the exponential of the level divided by that ML function or value that I mentioned earlier. So that's the multi-level, the level multiplier value. And what we get is a probability for the current level. Now, what we do is once we reach a particularly low probability, we stop creating new levels. So if we run this, another actually interesting thing is here, we are saying on every level, we will assign M neighbors as our M max, except from level 0, where we will assign 2M. Okay, so this M times like 2. So for our use case, we had 32. We had M set to 32. So that means in all of our layers, except from layer 0, each vertex will have 32 neighbors or friends. And on layer or level 0, it will have 64 friends. So I thought that was also interesting. So we can go ahead and run that. So the 32 here is our M. We can replace it with M if we want. So we run that and we get this probability distribution. So this is for layer 0, the probability of it being added using a random number generator. So we're saying if our randomly generated number is less than this value, we will assign or we will insert our vertex at level 0. And then we continue that logic all the way down to here, which is our level 4. And then here is the total number, so the cumulative number of neighbors per level. So if we insert at level 4, we will have this many neighbors for that vertex in total. If we insert level 0, we have 64. Again, a little bit interesting. Now, in the code, when we're inserting vertices, we use another function. This is the last one. We're not going to go through all of them. We're just going to go through this one. We insert, or we decide where to insert our vertex using this function here, which is the random level function. This takes our assign probas from up here, so this here, and also a randomly generated number. So here I'm using the NumPy's random number generator. And we go through, and that's how we assign a different level for each of our values. So let's run that, and we'll see that we get a very similar distribution to what we get in Faiss, which is, I think, pretty cool to see. So if we do the bin count again, we get this. Now, if you take a look at this, these values are so close to what we've produced up here. So where is it? So here, look at these values. Almost exactly the same. So yeah, it's pretty close. They're both working in the same way. Now, I also visualize that in this chart here. So you can see, okay, on the right we have our Python version, on the left we have our Faiss version, and I've included the numbers in there. Basically, it's pretty much exactly the same. It's off by a few here and there, but not much. So I thought that was pretty cool to see. Now, okay, that's cool. That's how everything works. That's interesting. But what I think many of us are probably most interested in is, how do I build the best HNSW index for my use case, for what I want? So I ran some code to go through all of that, and pretty much I did this. So we have, this is also a good thing for me to show you, is how we get our EF construction and EF search values. So I think, a good starting point for both of these values is, I don't know, probably 16, 32 is reasonable. But you can play around with them. I think that's usually the best way. And for most of what I'm going to show you, I was using this. So I was performing 1,000 queries and calculating the recall at one value for those. Also, I was checking, how long our searches are taking and the memory usage of each of these indexes. So the first thing I want to look at is a recall, of course. So in what we have here, on the left we have with a EF construction value of 2, which is very low. I don't know, never use that. Never use an EF construction value that low. Well, you can see the recall is pretty terrible. But, surprisingly, even though this is a very bad EF construction value, still got up to 40% recall. So I was impressed with that. That was cool. And so the EF search values are what you can see on the bottom. So it went from I think 2 all the way up to 256. 256, yeah, that's right. And we did that again for the EF construction value of 16 here, and also 64. I did it for more EF construction values, but these were probably the ones that I think showed the relationship best. And then all the colors you can see here, we have a few different colors. We're using different M values. So what I found from this is that you want to increase your M and your EF search values to improve your recall. And EF construction also helps with that. So higher EF construction value means that we need lower EF search and M values to achieve the same recall. Now, of course, we can just increase all of these and we get better recall, but that isn't for free. We have to sacrifice some of our search time as well, as always. So this is what we've got. So same graphs as last time, but this time we have search time on the y-axis. Now, EF construction here, it does actually make a bit of a difference when we start using higher M values. So I found before in previous videos and articles that EF construction didn't really have too much of an effect on the search time, which seemed fair enough because it's mostly a index construction parameter, but that it does seem to have some effect when you start adding or increasing the number of queries that you are searching for, and in particular where you have high M values. Now, one thing to also to note here is that we're using a log scale on the y-axis, so the high values are definitely a fair bit higher. But again, I mean, if we go for a sort of reasonable EF search value, all of these are pretty high. I mean, 256 for EF search values is high. If we go for sort of EF search of 32, let's say around here, we're still getting reasonable search times. So this is on the millisecond, well, it's a bit more than millisecond scale. And if we take a look at that on our recall, we're sort of getting up into the sort of 60 plus area at that point, 60% plus. And look, obviously it's not bad, it's reasonably good, but you can definitely get better than that when we start merging different indexes, which we have covered all of that in another video, another article. So you'll be able to find that in the either at the bottom of the article if you're reading the article, or in the video description if you're watching us on YouTube. Now, having a look at the EF construction values again, their effect on the search time, we find that EF construction, when we use those lower M values like I mentioned, it doesn't have too much of an impact on the search time. So if you are using a lower M value, I think EF construction is a good value to increase because it doesn't tend to push up your search time too much. And you can improve your recall a fair bit by increasing it. So it's definitely one to try and increase them and see how it goes. For me, I found it's been quite useful, at least. And then finally, the sort of negative point of HNSW is the memory usage is just through the roof, as you can see here. So using the lowest M value, which I think was 2, which is you would never ever use that. We were getting a memory usage for the SIFT1M dataset of more than half a gigabyte. If you push M up a lot, I mean 512 is maybe a little bit too much, but we're sort of pushing 4.5 gigabytes, 5 gigabytes. So it's something to be aware of, I think. But like I said before, we can still improve the memory usage and the search speed by simply using different indexes alongside our HNSW index. So if memory usage is a concern, you just compress the vectors using product quantization. If the speed, if you need it to be even faster, you can use an IVF index on top of HNSW to improve the search times. And if you want both of those, you just put them all together and you can get that as well. Now, like I said, we have covered all of that in a lot more detail in another article and video. But for this video on HNSW, I think we're going to leave it there. I think we've covered plenty. So thank you very much for watching, and I will see you in the next one. Bye.